optimal choice of lag orders. We were talking about the optimal choice of lag orders, where we were talking about Akaik's, Hanna, and Schwar's Bayesian criteria. Let us continue from where we left off. And so a Varma PQ model looks like this, and the log likelihood function hence is minus n by 2 1 plus log twice pi minus half of log of determinant of the variance covariance matrix V. Or we can put 4, we can put the equation 4, we can use this equation and replace the elements of log likelihood with the variance covariance matrix only. In case of a Varma model, the Akaik's, Hanna, and Schwar's Schwar's criteria looks like log of determinant of the variance covariance matrix plus the second element for all the cases remains same. As I told you, as I just talked, that Akaik's has only k, Schwar's has log of k log of t minus s added, and then Hanna has k log of t minus s with a log, additional log. So that is the 3 criteria. In case of scalar, we just replace the determinant of the estimated covariance matrix with residue variance sigma square. The step to choose an optimal lag order. Number 1. First, we need to choose a maximum number of lags for AR and MA components of the time series model. Respectively, the maximum number of lags P max is greater than P naught and Q max is greater than Q naught, where P naught and Q naught are true but unknown lag length. The choice of Pmax and Qmax is informed by SCFs and PSCFs of the date, the observed frequency of the data, sample size, etc. etc. Systematically, number 2 is systematically estimate the model for all combinations of lag orders where sample size t is fixed. For var p estimates, the model var p estimate the model sequentially for p equals 1 to p max. For VMAQ 1 to q max, Varma PQ estimate for all combinations of p equals 1 to p max and q equals 1 to q max. For each regression, the relevant information criteria are computed. Number 3, choose the specification of the model to the minimum values of information criteria. Basically, in a nutshell, we look into Akaik's information criteria in most cases, and the lag order is determined by the minimum value of the information criteria. Wherever the minimum value is located, we just take that as the highest lag order. For example, lag length of a AR3 model. Consider y equals 0, 0.2 yt minus 1, 0.15 yt minus 2 plus 0.05 yt minus 3 plus vt. This is a AR3 model where v is the IID. The model is simulated to generate 300 realizations of yt using starting value t equals 0 for the lag, 3 lags. The first 100 values are discarded to reduce dependence on initial condition, obviously just as before, and t equals 200 is used for simulation. AIC, HAC, and SAC are used to select optimal lag order in 2000 replications. Here, Akaik's and Hanna selects 2 lags, Schwar's selects 1 lag. Schwar's penalizes additional variables more harshly than Akaik's because in Schwar's we have more components, k log t divided by t, which is greater than which is greater than archaic 2k by t for t equals t equals or greater than s. So basically we would generally go for 2 lags instead of 1 lag because archaics and HANA is what we are looking into. We could select 2 lags in this system. Now distribution theory. Let theta naught, the true population parameter, be the true population parameter. Yt is stationary and martingale difference squares. Central limit theorem conditions are satisfied. Asymptotic distribution of maximum likelihood estimation is root over t theta hat minus theta naught. Asymptotically has zero mean and inverse of Hessian OPG multiplied to inverse of Hessian. This is the variance covariance matrix. Now Hessian itself is expected log theta naught. This is Hessian of theta naught, and the OPG outer product gradient is g theta multiplied to g theta transpose. We're already familiar with the gradient. Distribution of an AR1 model. AR1 model looks like yt equals 5 yt minus 1 plus vt is just a AR1 model. The gradient and the Hessian of the log likelihood function at t in the case of phi r. Gradient is vt divided by sigma square yt minus 1, or we can write further that yt minus 5 yt minus 1 multiplied to yt minus 1 divided by sigma square v. Okay, so instead of v we can write yt minus 5 yt minus 1, so vt yt minus 1 divided by sigma square, or yt minus 5 yt minus 1 multiplied to yt minus 1 divided by sigma square, and log theta becomes y square minus 1 divided by sigma square variance. Maximum likelihood estimated is the sample correlation coefficient phi hat equals r1. The sample correlation coefficient is yt minus 1 divided by y square minus 1, t equals 2 to t, because we have lag 1, so s plus 1 basically 2, t equals s plus 1, which is 1 plus 1 starting from 2 to t. Letting theta equals phi naught, which is population parameter. From definition of variance of autoregressive parameter, we have Hessian equals expected value of y square minus 1 divided by sigma square. Expected value of log theta. Log theta is y square minus 1 divided by sigma square. Log t is y square minus 1 divided by sigma square. We put that in. And we have expected value of y square minus 1, which is 1 minus 1 by expected value of y square minus 1 divided by sigma square should be y square minus 1 should be sigma square divided by 1 minus phi naught square, right? 1 minus phi naught square, which is the regular representation of autoregressive parameter, phi naught square, and this part remains as it is, so sigma square divided by 1 minus phi naught square. we're ending up with minus 1 by 1 minus phi naught square. Regress yt minus 1 on yt to get theta naught. As negative Hessian equals OPG, the asymptotic distribution R1 is root T R1, so we had root T theta hat minus theta naught. Instead of that, we write root T R1 minus phi naught. Asymptotically, that has 0 mean. Variance is negative Hessian, 1 divided by 1 minus phi naught square. Inverse of Hessian plus multiplied to OPG, which is the negative 1 minus phi naught square, and again inverse of Hessian. So we have MSC, mean squared error, which is theta hat with some likelihood minus phi 1 whole square divided by t, and root mean squared error is simply mean squared error root over. Mean is theta hat by t, biasness is theta hat minus phi 1 divided by t, with 0 mean 1 minus phi naught square variance. Mostly we need to remember the distribution to do our distribution example. Mostly we need to remember whatever we have just discussed here, right? So mostly we have to understand the gradient representation, the log t, it's not log t, it's actually ht, Hessian representation, and how we present that to identify variance covariance matrix representation, mean squared error, root mean squared error. In the special case where autoregressive parameter phi equals 0, the asymptotic distribution is root over t r1 with 0 mean 1 standard deviation. Now let's move into talking about testing. LR world and LM test for hypothesis on parameters of ARMA and VARMA models. We have many uses for LM for its easiness under null hypothesis. So for example, consider testing for independence of y on autoregressive parameter. So whether our dependent variable is so we want to know if our dependent variable is independent of autoregressive parameter or not. So if our ER1 model we are talking about, we want to know if phi is 0 or not, the significance of phi autoregressive parameter, where V is IID with 0 mean and sigma square variance. So we want to test the restriction of phi 0 or not. Okay, moving forward, we have just said that autoregressive parameter phi phi hat asymptotic distribution which equals R1. Evaluating the distribution under null is R1 asymptotically has 0 mean 1 by t variance, suggesting suggesting that LM test is independence. The LM test is based on root over t R1. Okay, we have just talked about that asymptotic distribution phi hat equals R1, and evaluating the distribution under null, we have R1 asymptotically having 0 mean and 1 by t variance, suggesting LM test is independent. That independence of LM test is based on root over t R1 with 0 mean and 1 variance, because t is the variance which is in squared form already. So root over t is taken here on the left hand side, so it's based on root over t R1 with 0 mean 1 standard deviance. LM test known to us has gradient transposed gradient and OPG inverse multiplied to t, or we have already dealt with this, where gradient is represented as zt vt hat divided by sigma square t, zt transpose divided by sigma square t, zt vt hat divided by sigma square t. One of them is in transpose, and taking the variances below t, under t we have this portion which represents r square, which is our coefficient of determination. Regressing v on z, we get this by regressing v on z t, which equals minus dt theta of vt, evaluated under null with chi-square distribution and k number of restrictions. We already talked about this in earlier chapters. I'm not gonna go into detail on this. However, in practical scenario, you'll see how we can measure this. Now, for example, we have LM. Let's have a look into LM test for a moving average model. Moving average 1 model, which is phi 1 yt minus 1 plus vt plus okay, let's test the ARMA 1 model. Phi 1 yt minus 1 plus vt plus psi 1 vt minus 1 for no moving average, because we are testing for a moving average. So let's set it a 0. Write the constraint model. So we are representing vt with yt minus phi 1 yt minus 1 psi 1 vt minus 1. The derivatives, z's are the derivatives. The first derivative again for vt with phi 1 is yt minus 1 minus psi 1 zt t minus 1. The second order derivative dvt against psi 1, so this one was against autoregressive parameter. Now this is d psi 1 of vt is psi 1 z2 t minus 1 plus vt minus 1, right? So because autoregressive parameter has is looking into variable and its own lags, while moving average parameter is looking into disturbance and the lags of disturbance of other variables. So we have z1 t minus 1, z2 t minus 1, and basically these are your two elements. So null is when psi 1 is 0, and putting that constraint, we do what? We regress yt on vt. So here we have vt equals yt minus phi 1 yt minus 1, z1t equals yt minus 1, because this portion is 0. With that we have z1t yt minus 1, z2t vt minus 1. That's all. When we put 0 against psi, so first we regress yt on vt, yt on yt minus 1. First we regress yt on yt minus 1 to get residuals of vt. Variance covariance matrix. Estimate second stage regression by regressing vt on yt minus 1 and vt minus 1, right? First we regress yt on yt minus 1 to get vt. Then in second stage regression we look into the z's, we look inside the z's, and looking inside the z's we regress vt on yt minus 1, vt on zt's. Basically we regress vt on zt's, and zt's are vt on zt, and zt is yt minus 1 and vt minus 1. We get r square, compute lm equals r square under null lm chi-square observation. So this is very simple, right? The trick lies in estimating z. That's all. And elements of Z is Z1t and Z2t. So the elements of Z are represented by the differential of Vt with respect to all the parameters under estimation, which are autoregressive and moving over H parameters. And basically first we need to regress Yt on Yt minus 1 to get residuals of Vt, then we regress Vt on Zt. That helps us to get R square, and then we put the values that we have computed into this equation, the R square basically. That gives us LM test statistics. Next is, so this was very simple, there is no trick, no difficulty. Next is analysis of vector autoregression. This section focuses on some of the tools used to analyze dynamic interrelationship between variables of VARs as outlined in VAR P. Yt equals mu plus phi 1 Yt minus 1 up to phi p Yt minus p plus Vt. As we know, Vt is IAD with 0 mean and V standard deviation. In specifying VARs, key determinants are numbers of variables, which is n, and numbers of lags, which is p. VAR represents reduced form of dynamic structural model, which is beta naught Yt equals beta 1 b1 Yt minus 1 plus ut, which is a reduced form approach. b0, b1 are the matrices of parameters. The n by 1 structural disturbance vector ut has properties where ut mean is 0 and variance of ut is the diagonal matrix of the variance covariance matrix. So is the simply the diagonal components of the residual is the variance. D is the diagonal matrix containing variance on main diagonal. The fact that D is the diagonal matrix means disturbances are uncorrelated. A restriction implied by structural model that is great, right? So disturbances are uncorrelated. They are diagonal, so that's a restriction in structural model. Expressing the system in terms of its reduced form, we are familiar with this. This is previous reduced form we had, beta 1 by beta naught Yt minus 1 plus ut by beta naught. Now beta 1 divided by beta naught, we can represent that with phi 1. So phi 1 Yt minus 1, and ut by beta naught, we can represent that with Vt, the structural residual, and that we get a var 1 model. So here phi 1 relates var and structural model. Structural parameter, so it relates var and structural parameter, and Vt relates var and disturbance vector. One cost of var is it generates relatively large number of parameters even for a small model. So var with n equals 4 and p equals 2 lags generate, as we are already familiar with, 32 autoregressive parameters, n square multiplied 2p and 4 constant. This issue can be circumvented with Granger causality, impulse response, and variance decomposition. Okay. Granger causality. A natural approach to understand a var is to determine if a particular variable is explained by lags of any other variable in the var other than its own lag. Again, I repeat, a natural approach to understand a var, Granger causality, helps us to determine if one variable is explained by the lags of any other variables in the var other than its own lag. So we test if parameters on blocks of lags are jointly 0, known as Granger causality test. So looking into a variable a, and we want to see if a is being explained by its own lag, but is it also explained by lags of b, c and d other variables? So we can jointly test the lags of other variables on a, and that is Granger causality. So generally it is convenient in terms of Granger causality, it is convenient to use wall test, and we are familiar with wall test equation r theta 1 minus q transpose r theta 1 minus q, and r, this is the variance covariance matrix representation estimated r transpose. Quick revision. Vector of autoregressive parameter estimates R, and vector of autoregressive quick revision is vector of unrestricted parameter estimates. Okay, oh sorry, not here. Yeah, theta 1 is vector of unrestricted parameter estimates. R and Q are matrices based on restrictions. So vector of unrestricted parameter estimates is theta 1. Unrestricted parameter estimates is theta 1, and R and Q are matrices based on restrictions, right? Theta 1 is unrestricted parameter estimates, and R and Q are based on restrictions. So null is if wall test W asymptotically, null is when the wall test is asymptotically a chi-square distribution. Degrees of freedom is number of zero restrictions being tested. Example, causality test for the United States VAR. In the VAR2 model of US, we have n square b 36 parameters ordered as mu1, and we have two constants as well, because that is VAR2, mu1, then 511, 1213 up until n square. We have four parameters. No, we have 1, 2, 3, 4. In VAR2 model, we basically have 4 parameters, n squared into p, 1 lag, no, 2 lags, VAR2 model into 2. So we'll end up with 36. We'll end up with 36 parameters. What we are going to do here, and number of constants are also added, we're gonna arrange all the parameters in index, and we'll determine which one will have 0 and which one will not. So 5111 is lag 1, as we have studied that before, lag 1 on equation 1 on variable 1. So here we have 2 lags for first equation, continuing my 2 where second equation begins. So up until mu2, this is all the elements of mu1 for 2 lags. Then we are moving on to mu2. So to test whether money fails to Granger cause the interest rate, denoted money, Granger does not cause interest rate, we need to know the position of money and interest rate. And 5112 is money fails to Granger cause interest rate and the lag of interest rate. First one is the main value, money, and the lag of interest rate equals 0. At least one restriction fails is alternative. To complete Wall's test, theta 1 is obtained by determining 2 by 36 and q, because 2 1. Q has 2 elements because two of the parameters will have 0 lags, because n square root over n, 6 variables, number of tests. So 1 2 3 4 5 6, right? We must have 6 variables here, right? Or 4, I'm not sure. We are supposed to have 4 variables. Yeah, exactly. 4 square into row 32 plus 4 constants, because 4 systems of equation will have 4 constants, hence 36. Very simple. Okay, so in we will have the constants appearing. Now, because it's Granger cause, for reverse causality, the whole thing will happen again, right? Because two things will happen in Granger cause. Besides putting all of them together, we have to also test for reverse causality. We'll understand more when we go on discussing in terms of smaller variables. So let's move forward. So up until now we understand, right? Up until now we need to identify number of parameters based on variables. Each variable will represent a system of equation and will have number of constant, and we arrange them in indices for causality, and for reverse causality we'll do them again and we'll check for zeros. That's all, very simple. Now still let's move on. Think about 3 variables, right? x1, x2 and x3. var1 of lag1 is var1 of lag1 is phi 1 1 xt minus 1 1 phi 1 2 xt minus 1 2 phi 1 3 xt minus 1 3. So we have 3 variables, xt1, xt2, xt3. This is the system of equation that we represent. Basically, in case there is var2, there will be 6 predictors on the right hand side plus constant plus the trend, right? Trend stationary models are detrended series or stationary. We do not need to detrend each series. We can include trend directly. S is equal to autoregressive parameters plus constant plus trend. Basically, trend is making sure that the system of equation becoming stationary. So a stationary model looks like this: 10 constants and the autoregressive parameters. So we have 4 variables. We are looking into a 4 variable system. 16, then 2 lakhs 32 plus constants 36. Each row should have 32 variables. Each row should have 32 variables plus constants, right? Yes, each row should have 32 variables plus constant. First, make a line with the line command, command. So we'll make a line from these matrix, reshape alignment, reshape A transpose in columns and rows. So there is a matrix A transpose. We are reshaping. This is one structure. Then transpose it for line, reshape it in A transpose, or otherwise we can do A transpose in 6 columns and 1 row. So A transpose columns and rows. For line, we are just representing the whole thing into 6 rows and 1 column, basically in 1 column. Now reshape it with reshape command. Basically for 2 lakhs, reshape the entire matrix to 2, so 36 rows will have 2 columns, will be easier to see because 36, because we are doing Granger Causality. We're doing Granger Causality, so it'll be doing 2 instead of 1, right? Now make zeros where you will put your restrictions. So this is the command, actually reshape matrix total number of elements, or you can simply give your matrix how many rows. You don't need to know, the system will automatically set. So in reshape we have column and rows, how many columns will appear, the system will automatically set. You just give the total number of elements. Good, that is a good way. You just give the total number of elements that you estimated, and the system will automatically create number of rows for you, number of columns for you, columns, and this is the number of rows that will appear. This is the easier way to represent to create that index, that is logical index that I was talking about. Then you can put zeros in all the index except for where you are putting restriction, that will be 1, right? That is in a nutshell what here I'm trying to say. Now put restrictions. Think about 2 variables only, money and interest rate. Say money, interest rate, Granger causes lag of money. Okay, so that will be money. First one is constant, then money, and a lag of interest rate. And then each step the block iterates forward. Used up blocks and used up blocks are never returned, so this is corrected. Money and interest rate. Then where else do you put ones? You keep on moving forward and keep restricting money and interest rate. We just need to know where the constant is, so every time we need to put ones against money and the lag of interest rate. This is a bit tricky, but this is a good way that we have just discussed. First, you can simply follow this criteria, right? To avoid all the confusion, you can simply parameters and lags. You can simply put, so you see here we have 1 2 3 4 5 6 7 8 9, total 36, right? But for Granger Causality this 36 will be presented again. So simply you can put your matrix and you can put total number of elements. Okay, and number of columns you can keep it empty, and MATLAB will determine that for you. Six column 1 row for line, 6 column 1 row, and then that can be transposed. Alright, so that is the basic. Did we do any further discussion? See, if we go up, we'll see how for this particular problem we decided where the restrictions will go. So first we had interest rate, prices to interest rate, output interest rate, then interest rate to money, price to money, output to money. Obviously this thing will happen again and again and again, so the indexes will be representing for each lag, right? This is not a good way to remember, but yeah, we can still look into that. For example, money to interest rate, lag of interest rate indeed, right? And then moving forward, interest rate to money. Now we start for interest rate and for money again, interest rate to money, okay, price to money, output to money. So you see what is happening here is the size of the that we have calculated, which is 36, is not being played here, because we are not looking into money affecting on Granger causing interest rate only, but we are also looking into if interest rate is also Granger causing money. So your 36 might be might end much before we start in the reverse causality testing. See, so in each column you should represent, so this is the first column, this is the second column. In each column you should represent how you are arranging your blocks, okay? So that's why this restriction goes up to so many numbers up until 36. Because of reverse causality, very simple, because of reverse causality, 36 is arranged into for 2 lags, 36 is arranged into occurring twice in terms of Granger causality, and that will be easier for us to simply remember. Basically, best way to remember this, because there is a reverse causality, we have 2 columns. If there was no reverse causality, in general we didn't need two lines. One line could have been fine enough, but we need 2 lines here because of reverse causality. That's all, very simple. We can manually set it up. Okay, then let's move on to discussing impulse response. The Granger causality test of previous section focuses on the lags of the VARs. Okay, so we wanted to see if in Granger causality, what is the definition of Granger causality. Basically, in Granger causality we wanted to understand in a VAR if a particular variable is explained by the lags of any other variables. In impulse response is to transform the VAR to VMA and identify the impulse response. Also wants to see if particular variable is being affected by the lags of a particular variable is explained by the lags of any other variables, but the method is to transform VAR to VMA and identify the dynamic properties of VAR from VMA. Now the trick here is we need to understand that this is a VAR system, not a Varma system, so we don't need to estimate maximum likelihood estimation. OLS is sufficient enough. Besides, OLS and MLE should give you the same results. So consider a VAR P where mu is 0, assuming stationarity. VMA is infinite dimensional. Okay, so it is Vt psi 1, Vt minus 1 psi 2, Vt minus 2 psi 3, Vt minus 3. Taking conditional expectations on 1 based on information at time t minus 1 and subtracting from 1 gives 1 step ahead forecast error, right? So 1 step ahead forecast error is simply Yt minus expectation on time t minus 1 which was yt et minus 1 yt, and we subtract it. So yt minus, so 1 vt minus 1 plus I2 vt minus 2 plus I3 vt minus 3, we end up with vt, residual variance matrix. At time t plus 1, yt plus 1 so equals vt plus 1 psi1 vt plus I2 vt. So time t plus 1 is 7 vt plus I2 vt vt minus 1 plus I3 vt minus 2. So this is yt, this is yt plus 1. One step ahead, forecast error variance is conditional expectation on taking conditional expectation on this based on information at time t minus 1 that we subtract from these. We have one step ahead forecast error, which is represented with the variance covariance matrix, and this is at time t plus 1. So vt affects yt plus 1 through psi 1, vt affects yt plus h through psi h. So to understand VAR, you need to analyze the VMA parameter, vector moving over each parameter size, right? Even for a VAR-P system, we need a VMAQ system to estimate. Interpreting the dynamics of a VAR system in terms of VT. Dynamic of VAR system in terms of VT in the equation of yt plus 1 is problematic because the covariance matrix V in general is a non-diagonal matrix. So disturbances are correlated. So it's the covariance matrix where your disturbances indeed are correlated in a non-diagonal because it's not a diagonal matrix, it's a non-diagonal matrix. Well, our residual variance was diagonal to each other. To circumvent this problem, we replace the structural residual VT by structural shocks. Structural shock is represented with ut, because vt equals ut by divided by b naught from reduced form we just talked about, because vt relays var and structural disturbance vector. The structural disturbance vector ut is represented as structural shocks. So first represent the model with dynamics of the VAR system. Basically represent the model with structural with the VAR. B naught is the VAR and the structural model is this ut plus psi naught ut minus 1. So instead of V, now with B naught you can represent this ut minus 1 ut minus structural shocks. We're bringing in structural disturbance vectors, but this is just shifting the problem. Structural parameter beta naught needs to be identified. Now the most common way to solve this is Sims method. Sims specify the structural VAR as a triangular matrix, so the contemporaneous relationship among variable yt is recursive. This is the implicit assumption in performing VAR analysis and reporting results in terms of yt plus 1, the in terms of this equation. So now we need to put Sims recursive specification. So what is happening in terms of code when we move forward each time t equals 1 to I by beta I j u y I j equals I minus 1, we explain that just recursive, this is a recursive moving forward. We remove earlier elements when we move forward recursively. So y1t, you have lags and you have the residual beta 2t y1t, beta 3 y1t plus beta 3 2 y2t, beta 4 y1, so y1, then y1 y2, then y1 y2 y3. So this is lower triangular matrix. We're ending up with a lower triangular matrix. So beta naught, beta naught in the equation of beta naught yt equals beta 1 yt minus 1 plus ut. Basically this is the reduced form equation, taking beta naught on the left hand side, the var, and d is diagonal element of the residual variance covariance matrix is repeated respectively located here, is diagonal. Now it becomes diagonal now. Now if the diagonal element of the residual is 0, the error or the eigenvalues are orthogonalized, so no correlation in our errors. If the diagonal element becomes if the covariance of ut transpose is 0, then the eigenvalues are orthogonalized. That means there is no correlation in the errors. And the diagonal elements are d11, the diagonal elements of the residual is d11, d22, d33, d44, which are the eigenvalues. If this is 0, if this turns 0, I mean if the relationship of ut transpose is 0, then this is orthogonalized and no correlation of errors are found. Eigenvalues are orthogonalized. So these are the eigenvalues. Diagonal of the var represent eigenvalues where the coefficients are located in a lower triangular manner. This is the specification of beta naught, or this is the specification of a var, only the var beta naught. And we need to identify beta naught when we are replacing Vt with structural disturbance vector ut. This beta naught is necessary to, I repeat, this beta naught is necessary to identify, because whenever we are transforming Vt to our Vt, converging the Vt to structural disturbance ut, okay, from the regular equation, regular vector moving average equation. So that is what we have done up until now. So whatever the steps that we have gone through up until now, the steps are: convert var to VMA for forecast error. We have learned that. We have been able to represent the our equation in terms of structural disturbance vectors or structural shocks that we replaced from structural residual, which is or the variance, replacing V, and we got the lower triangular matrix for beta naught. We specify our beta naught in lower triangular matrix. We need to remember the diagonal elements are where the eigenvalues are located, and if ut transpose is 0, then there is the eigenvalues are orthogonalized, which means there are no correlation in the errors. Estimate the triangular matrix in whose diagonal vector we have the structure shocks. So we need to estimate the triangular matrix where in the diagonal elements we have structural shocks or the impulse responses. If again ut transpose 0 means orthogonalized, there is no correlation So if we don't have any relationship in structural elements, there is no impulse response. Impulse response is looking into if disturbance vectors are affected by the disturbance vectors of the other variables. Given the recursive nature of the structural model, we can estimate the model parameter in 4 possible ways. Structural approach. So what are the approaches? We need to estimate the model parameters, beta parameters. First, we do structural equation because it's a VMA. Each structural equation we can estimate by OLS. Each equation, you see, you can combine them later and that will give you same as maximum likelihood estimation. So each equation can be estimated by OLS, y1t, y2t, y3t and y4t. These are the equations that we need to remember. The ith element of d hat is computed as v square by t. U square by t is simple. The diagonal element is computed as u square by t. One. So what is happening here? First is 1, nothing is there, then 0.053, then 0.027, 0.387, these are beta, then beta 1.13, and the next one is 0.013, there's no use of this one, and 0.112, then the next one is 0.042. So this is how we arrange beta parameter, and the diagonal elements are then simply the decomposition. Diagonal elements are estimated. We compute the diagonal elements as summation of u square divided by t. Then reduced form approach. The next method is, first method is OLS, the next method is reduced form approach. We estimated by OLS, estimate by OLS to yield estimates of VT hat, which is the structural residual VT hat. We rewrite VT as the we rewrite by decompose VT. The structural residual is represented as structural disturbance or shock. Structural disturbance or shock related with the VAR, or we can rewrite this gives us recursive structure in VAR residual. This should give us, because beta naught is lower triangular, okay, we specify beta naught as lower triangular multiplied to structural residual. If we do that, that means our structural disturbance will be also lower triangular, and we get a recursive structure in the VAR residual. Now replace VT equals V1, V2, V3. I mean, replace VT by estimated VT hat and estimate equations, the VAR residuals, and estimate equations with OLS. Okay, so basically this is easy. As we multiply that, our estimated parameters are, well, simply the representation that I just talked about, the matrix that you have. Now we are thinking that matrix to be the matrix that you have just found. Each row of the matrix represents is equal to structural the VAR residual. Each row of the matrix equals to one row of the VAR residual. That's all. So you already have specified the lower triangular matrix beta naught. Okay, with a recursive process in a lower triangular matrix. Then you multiplied that with Vt, which is your structural var. When you do that, each row of your matrix represents one estimated structural var, that is equal to your estimation of structural residual. So that is what it is, right? So the estimate of structural variances computed from these residuals, so the structural variances, this is structural variances computed from the residuals, are used to calculate the diagonal matrix d hat. Okay, so from here we simply find sigma square v divided by, I think, t, that gives you the diagonal elements. So we can decompose this anyway to get the diagonal elements. Very simple. So this is the reduced form approach. Very simple. We just need to, for reduced form approach, we just need to multiply our structural residual Vt with beta naught, which has been specified before. Then Cholesky decomposition. So again, for this we need to estimate each equation with OLS. We use var residuals to compute v hat in this case. And a Cholesky decomposition of v hat is performed as v hat decomposed, and each composition is S transpose. So estimated, each equation of var is estimate with OLS. Okay, obviously, so we get the beta naught, and then we multiply with var residual to get v hat. Okay, so we combine first one and the second one, reduced form. Basically we do up until reduced form approach, and then we decompose it further. The reduced form, we decompose it further so that we can get two matrices out of the reduced form structural var residual matrix. Now we want to recover beta naught from S, right? If we want to recover beta naught from S, we just need to define the structural variances as squares of the diagonal elements of S. We just need to define structural variances as squares of the diagonal elements. So squares of the diagonal elements of S helps us to find beta naught. So squares of the diagonal elements, we take the squares of the diagonal elements. So what we did here in Cholesky decomposition approach, first we did up until reduced form approach. So first we identified beta naught, we multiplied beta naught with structural var residual, and we get the structural var residual matrix. Okay, and then we decompose that matrix into two matrices, smaller matrices, and which are S. Each decomposition is S, and then the diagonal elements is structural variances, and then we have, as we know, V equals Vt transpose, the structural var residual, or the structural variance. We have already estimated the structural variance. The structural variance equals structural var residual Vt transpose, or Ut by beta naught transpose. So, or beta naught transpose inverse Ut transpose, which is the diagonal element. We already have beta naught inverses, and we already have diagonal element. So S is equal to root over d by beta naught. S is equal to root over d by beta naught. That is the relationship, right? Beta naught inverse d beta naught inverse transpose gives you V. We already know S is equal to root over d by beta naught, or beta naught equals root over d by S. So basically this is the process of finding beta naught, which is root over d divided by S. That's all. And we already know S, but still we can find S, which is root over d by beta naught. So structural variance is VT transpose, which is the structural residual squared. Structural disturbance presented with is VAR squared. That's it. Beta naught inverse d beta naught, and that helps us to find S and beta naught. Or beta naught can be represented with simply root over d by S. That's all. Or we can write it as SD inverse root over d inverse. We can write this as this equation. So if we do calculate, we get back our beta naught. Common in all approaches is we transform VAR to VMA, and then with the help of VMA we represent our equation with beta naught, right? We take the reduced form approach suggested by Sims. We represent our model with structural shocks, and then when we identify our equation in a lower triangular matrix, we find eigenvalues. We estimate our equations with OLS, each equation with OLS to get beta naught and structural residual. Then we find our residual matrix and get a diagonal matrix. For Cholesky, we decompose it further. The structural variance is decomposed further, where each element has S, and we take the diagonal elements of that too. Then comes maximum likelihood approach. VAR is estimated, so we do estimate VAR with OLS again, because it's VAR, the main system is VAR, so we do estimate OLS, and we estimate up until structural variance, right? Then we maximize the log likelihood function, which is half log test by half log v 2t minus 2, because we are talking about var 2, so it's plus 1 3 v variance, structural variance, and vt, which is maximized with respect to beta naught and d. Well, v is equal to beta naught inverse d beta naught inverse transpose. We already know it, and so we get estimates of beta naught and d as before. We also get standard error based on Hessian. So basically, if we solve for it, we get beta naught. This is the restriction, so subject to restriction. So we get beta naught and d automatically with Hessian in parenthesis. The advantage of using maximum likelihood estimates is that we get additional, the results remain same, we get additional standard errors that help us with hypothesis testing. Cholesky gives us only 1 point estimate. Now we have structural variance, we have structural residual or structural disturbances. Structural variance matrix, the variance matrix is a square matrix. We have structural disturbances, which are non-squared disturbance vectors. This should allow us to find structural shocks or standardized structural shocks. Standardized structural shocks are represented with ut divided by root d, ut divided by root over d, which is standardized structural shocks. So one by d represents diagonal matrix with structural standard deviation down the main diagonal. So 1 by d here representing diagonal matrix with structural standard deviation down the main diagonal. Okay. All right. So standardized structural shocks are structural disturbance divided by root over diagonal elements of the matrix, or 1 by d represents the diagonal matrix with structural standard deviation down the main diagonal. Now, so we can write, we already have written yt thus in the reduced form of ut beta naught 5 psi 1 ut minus 1 beta naught. So this is the equation we have already represented previously. Now instead of that, we can rewrite the equation with the standardized structural shock, which is, instead of ut, we can write zt root over d. So in place of ut, we can keep on writing zt minus 1, zt minus 2, zt minus 3. We know s is equal to root d by beta naught. That is known to us, so we put s, which is we collect with decomposition in place of, you know, vt. So s zt ut by beta naught. Instead of that, we write s zt psi 1 zt minus 1 s, psi 2 zt minus 2 s, psi 3 zt minus 3 s. The parameters in current zt and lagged zt. So the parameters are current zt is s, and the lag zt is psi 1 s, psi 2 s, etc, etc. So this is important. Each parameter represents one standard deviation orthogonalized impulse response function. So this is one standard deviation orthogonalized impulse response, and parameters, each parameter psi 1s, psi 2s, they represent one standard deviation orthogonalized impulse response function. And then, so here it is. So what happened up until now is that, see this is the impulse response function, one standard deviation orthogonalized impulse response function psi h minus 1s. So what is the development up until now? Let's see. So first we have a VAR equation, and we know that VAR cannot do not require maximum likelihood estimation. With OLS, you can simply estimate VAR. Each equation in a VAR system, in the systems of equations, can be estimated with OLS, and it will still yield the same result. So to begin with, we have a VAR equation. We convert our VAR to VMA, and we have VMA representation with structural errors, structural variance, and then we also use our estimated VMA to find forecast error. Then next is that we change our VMA structure we represent the VMA equation with the help of reduced form equation, replacing our structural errors with structural disturbance vectors. And structural disturbance vector well, is contemporaneously related with the VAR matrix beta naught. So we need to specify that matrix, and to collect is recursive algorithm, recursive structure. We apply lower triangular restriction suggested by Sims. We estimate each coefficient or each beta parameter, each beta coefficient with OLS, and also simultaneously we estimate residual variance covariance matrices or residual variances V with OLS as well. So we have beta matrix and which is lower triangular, and we use its diagonal elements where eigenvalues are located diagonally, and we use that to find the variance of the matrix, right? So we go into four methods. So first method, structural equation approach, up until whatever I talked about. Then reduced form approach is that now instead of using well, we simply what we do is we found beta naught, and we also found structural variance V, variance covariance. Basically we multiply them together and we get a residual disturbance, structural residual variance covariance matrix V, right? And that is also restricted, that gives us a lower triangular matrix, which is a structural variance matrix. Good. So from structural error with the help of disturbance vector, well, you get structural variance and coefficient and beta matrix. You have two matrices, beta and S, beta and V now, right? Now, and also D. We have also estimated D. Now we take it further. We decompose V, our structural variance matrix, or the variance covariance, basically the variance covariance matrix. We decompose it and we get two S's, S, and each S is one decomposed matrix. And now we also take the diagonal elements of S. We can revert back to B naught from S, because S equals simply root D divided by B naught, and D is the diagonal elements of S. Well, B naught is root D by S. You do that, you get back B naught, or S is root D by B naught. If you have D and B naught, you can still find S. So up until this is fine, this looks very good. And now we want to move even further, right? So we can use MLE, maximum likelihood estimation, as well. And if we do maximum likelihood estimation on a log likelihood function with the determinant of variance covariance matrix in, which is also represented as B naught inverse transpose D, B naught inverse, right? Because it's a variance covariance matrix, so B naught inverse D, B naught inverse gives you basically the same thing, because standard deviation, 1 by D is standard deviation, so sigma square divided by the coefficient, basically. Okay. So we can find beta naught and D with maximum likelihood parameters with maximum likelihood estimation, as well as standard errors with maximum likelihood estimation approach. Now we have we can also find our standardized structural shocks with ut divided by root D function. z is equal to ut divided by root d. So using this equation we can rewrite our reduced form as sz(t) psi 1 zt root d by b naught zt minus 1 root d by b naught. So we can replace our reduced form equation wherever ut was with zt root d, and root d doesn't change in terms of lags, but zt does, and root d by b naught is something that we find everywhere. So we know root d by b naught is s. We can do that and we get a structure which is psi h minus 1 s, and that is what our one standard deviation orthogonalized impulse response function. So you see, we derive up until v with OLS, and then we can simply find impulse response function with psi h minus 1 s with all the parameters estimated. That is what we have discussed up until, which is quite simple steps. We just need several parameters, and impulse response function is basically d dz yt plus h minus 1. So basically this. So we use an example for impulse response. We move further with variance decomposition. So consider a two Var2 estimate with n by 4 h equals 1. The one standard deviation impulse response function would be psi naught s, right? Which is I4 s hat, or simply s hat. We already know it. So lower triangular representation. The impulse response when we do h2 equals psi 1 s hat. Basically we move forward. We take this down here and here as well, because psi 1 is, I think, psi naught and psi naught. No, sorry, s comes down as it is estimated, and we put the value of psi 1 estimated psi 1 hat here, and we have impulse response function 2. So we go do this for h minus 1. For this example there are 16 impulse response functions for each h with the effects of an interest rate shock of n equals 4 variable given in first column, the effects of money shock in the second column. Impulse responses are non-linear functions of estimated VAR. Use three approaches to compute standard errors: delta method, Monte Carlo technique, and bootstrapping. So delta method, Monte Carlo, and bootstrapping are the techniques that are used to find standard errors in impulse response functions. Important to remember for now. Okay. Now variance decomposition. The one standard deviation impulse response function gives the conditional mean of the distribution of the dependent vector. The variance decomposition, on the other hand, is concerned with conditional variances of the impulse response function. So we have talked about conditional mean now of the impulse response function. Now we want to do variance decomposition, which should give us conditional variances of the impulse response function. The VAR at t plus h is, we know y, so we know about yt, which is sz psi 1 sz. Well, the equation was sz minus 1s plus i2 sz minus 2. So this was the equation, right? sz. Now we do yt plus h, we add plus h. So everywhere we get plus h, that's all. And when we do that, we also take an expectation on the conditional mean here, and we have sz plus h, which equals psi h sz, psi h plus 1 sz plus 1, psi h plus sz plus 1, psi h2 plus sz plus 2, which is, from the properties we can write this as well, psi h SZT, psi h1 SZT plus 1, psi h2 SZT plus 2. So it will go on like that, right? So the conditional variance is decomposed as, the variance decomposition is yt plus h minus expectation of yt plus h. So this one is the t plus h minus psi h as the t, this one, and then again this one transposed. Very simple. As the t plus h plus psi h, or psi 1 as the t plus h minus 1 plus psi 2 as the t plus h minus 2. Okay, this will go on and on, because this goes up until h, that's why. And we multiply it again and do transpose, and we have variance decomposition. That's all, which is a complicated equation, but it is still the same equation. So it's just simple. We have the regular equation with plus h, then we have an improved equation, and then we take the difference, okay, for all the parameters, and we add them, and we squared that, that's all. And ultimately that gives us the variance decomposition matrix. Ultimately can be written as, for I equals 0 to h minus 1 psi I s transpose psi I transpose. This is what we derived to for I equals 0 to h minus 1, with the first one being the first moving average parameter being the identity matrix. So psi I s, that looks like an impulse response, right? That looks like an impulse response and multiplied to impulse response transposed, right? Very, very familiar face. Basically, you are correct. Impulse response and impulse response transpose. So this is already an impulse response function multiplied to another impulse response function, element by element, which is Hadamard. That is variance decomposition. That's all, right? Very simple. Two impulse response function multiplied, and the first one is in identity matrix. The last step follows EZ2 transpose identity matrix by definition. Alternatively, this equation can be written in terms of separate contribution of each of n shocks. This equation written in terms of separate contribution of each of n shocks in the system to h step ahead variances. So we can say each shock, we can the contribution of each shock. Variance decomposition captures the contribution of each shock on the h step ahead variances. H step ahead forecasted of variance decomposition means the contribution of each shocks in the system to the h step ahead variances. Very important to remember. So you see this is I equals 0 to h minus 1. So psi I s1 s1 psi I s2 s2 psi I s3 s3 psi I. So psi I does not change, s continues to change, right? S1 s2 s3 for h equals 1 to 3. Psi I on the other hand remains same, where si is the ith column of s, and even simpler expression is through element by element multiplication. So we already know what a Hadamard is. I'm not going to go into detail. And so we have variance decomposition, beautiful, which is again by definition contribution of each shock, which is coming from Z, standardized shock, right, in the system to h step ahead variances. Okay, So basically this is it. The total variance of each variable is given by row sums of the each variance decomposition, with the elements representing the contribution of each variable to total variance. I mean contributions of shocks from each variable to total variance. So the total variance is given by total sums of the rows, where we capture the shocks coming from each variable to the total variance. For example, total variance of h equals 2 step ahead. Forecast error is output is given by last row of variance decomposition 2, which is 3.20. Contribution from all of them, the shocks from all of these variables to total variance. So here we kind of conclude the theoretical part for now, and we intend to move into our applied portion, which was a fun journey up until now, and we talked about very important concepts. Basically, one essential thing to remember from a given system of equation, how we can derive up until impulse response functions, changing primarily estimating coefficients, important coefficients or beta naught. That helps us to find our variance covariance matrix V, or which is the structural variance matrix, and also helps us to find structural disturbance vector and the diagonal elements of the vector that plays important role. All of these allow us to in 3-4 steps, actually 4 different steps, eventually drive us to estimate impulse response function. And the impulse response function on the which by definition impulse response function is mean, basically conditional mean of the distribution, where in impulse response function we wanted to check the effect of the lags of so in impulse response function, basically we wanted to check the dynamic properties of VAR from VMA. So basically we wanted to check how structural shocks are affecting each variable. So if one variable is being affected by the structural shocks from other variables and lags of other variables, that is our impulse response function, right? And also we talked about Granger causality. Basically Granger causality and impulse response function, both of them almost give us same definition, which determine a particular variable if that is explained by the lags of any other variables other than its own lag. And then we used impulse response function squared to find variance decomposition, which is now this time one standard deviation impulse response function giving conditional mean, and we estimate conditional variances with variance decomposition. Okay, and we define variance decomposition as contribution of the shocks from each variable to his step ahead variances. Instead of directly talking about variables, we talk about variances. So here we end the theoretical part of one of the most important chapters in econometrics, and we'll see you with applications. Thank you.